Okay. So, for those who don't know and haven't read my emails, this is Tracy Becker. She works at the Southwest Research Institute in Texas, San Antonio, Texas, I believe. And she works on a lot of cool stuff, including studying asteroids and Saturn's rings and introverted moons with UV light. And she's working on a new mission Europa Clipper, I think. It's going to be launching soon, so that sounds pretty cool. But I'll leave the floor to her. And let's hear what she has to say.
Oh, I just realized I hadn't tried to share the screen until now, and I need your permission to do so.
I think you should be able to.
All right, let me share. All right. So yeah, hi everyone that's in the room, and if people end up watching this later on, hello to you all. Yeah, so my name is Tracy Becker. I was a student at Lehigh. I was technically class of 09, but I graduated in 10, and I'll explain a little bit why that happened. But I'm really, yeah, I'm excited to give this talk, especially to SPS, because I don't know if SPS existed before 2008. I don't know if we started it or it was just like in a hiatus, but I was part of SPS at Lehigh once upon a time. So this is the group of students that were around at that time up there. And I also put this picture on the bottom right because I think Alan gave a talk a couple weeks ago for you guys. Is that true?
Yeah, he said to say hi.
Yeah, so he reached out to me. I hadn't heard from him in a long time, but it was great working with him and with a lot of the other students most of them went off and did cool stuff since then. But yeah, so this is what SPS looked like back in 2008. But yeah, so really quickly, an overview of what I do and what I'm doing is, like Daniel said, icy moons, asteroids, and planetary rings are sort of my main science focus. But I'm currently a lead scientist and group leader at the Southwest Research Institute here in San Antonio. And my NASA mission involvement has been pretty extensive since I've been here at the Institute, at Southwest Research Institute. So I'm currently the deputy principal investigator, which is basically the second lead for the ultraviolet spectrograph instrument on NASA's Europa Clipper mission, which launches in just a few months in October of this year. I'm also the deputy principal investigator for the ALICE instrument, which is another UV instrument on NASA's New Horizons mission, which is the one that flew by Pluto a couple years back and flew by some Kuiper Belt objects since then. I'm involved in the European Space Agency's JUICE mission through our UV instrument. You'll see a trend of UV science going on here. When I was a graduate student, I was involved with the ultraviolet instrument on NASA's Cassini mission to Saturn. So that's where I kind of got my science start. And I worked on NASA's Juno mission. I'm currently working on NASA's Juno mission as a lead for the satellite working group. So I've recently been brought in on that to help organize sort of all of the science going on related to the satellite flybys. But I also use Hubble Space Telescope and the James Webb Space Telescope. And I used to use the Arecibo Observatory in Puerto Rico. And if you all have any questions, just feel free to shout and interrupt. So yeah, like I said, SPS back in 2008. And so Daniel asked me to kind of give an overview of sort of my career and how I kind of got to where I am. So I'm one of the people who, you know, as a kid discovered space and fell in love. So in second grade, I read a book called I Can Read About the Sun and Other Stars. And later on, I bought that book off of Amazon because I remembered that was like the book that sparked my interest. I got really into writing my own books about space. That was like what I enjoyed doing, was like learning about space, but then sharing it. And you'll kind of see that theme throughout this presentation, but I really do like to communicate science as well as do research. Um, and yeah, if you are saying something, just shout because it might be a delay. And then in 5th and 8th grade, I got to go to space camp. So that kind of also helped. Although I learned then at that time that I was too short to be an astronaut, which was kind of a bummer, but it's okay. And then now the new astronaut policies are much more wider. So if you want to be an astronaut and you're only 5 foot like I am, I think you still can apply. But then in high school, I joined a magnet program for global languages and cultures. So even though I had this like really intense interest in space, I didn't always do things that were specifically space related. And I think that's generally helped me. And that's sort of one of the themes of the presentation that I hope you kind of take away. One, I love doing what I'm doing. I'm so glad that everything has worked out the way it has and that I get to be involved in all these NASA missions and do all this cool research. But that the extra non-science work that I've done, so this focus on like global cultures and languages and other, outreach and other activities like that, actually, I think are the reason I get to do what I get to do every day. So keep following any idea that interests you, and there's no one path in your career, because your job is going to keep evolving. So just kind of keep that in mind, and you'll see sort of those themes pop up, I think, as I kind of describe my career path at least. So Lehigh University, my major was astrophysics, but my minor was Latin American studies. So there you can see that theme already again, is that while I was taking classes, in Lewis Lab, doing all the physics, math classes that I had to take, I actually really enjoyed having that separation with some of my classes that were involved in like, watching films in Spanish to learn, and having anthropology courses and things like that. And, I found the physics classes at Lehigh to be very hard. At times I definitely considered just changing careers because I was naturally better, it felt like, at some of the other classes I was taking. And so I thought about it. But I stuck with STEM in the end. Um, I put in some places when I was a freshman. I lived in Carruthers. Sophomore year, I was in Drinker. And then I lived off campus on Lawfer Street, and you can see some of my friends down there. I actually had two of my really close friends from Lehigh come visit me last week because the solar eclipse went right over my house. So they came out with their family. They were two of my colleagues, two of my friends that ended up dating at Lehigh and getting married afterwards. So or staying together at least forever, and they have kids and all that. So Lehigh can be a place, where you can stay with some of those friends forever, really. And even though they live in Oregon and I live in Texas, we keep in touch, which is nice. But yeah, I needed that balance with the classes I was taking as my minor, and then some of the extracurriculars that I'll talk about too, which I think again really helped me in my career. Like all of these non-science parts really helped my career. I was a work study student. I worked at the Multimedia Center. I don't even know if that still exists on campus, but it was a place where you could come and rent films that you needed for your class, and it was also there were people there developing some of the like programs, computer programs for the university. Yeah, I don't know if it still exists, but I joined the RHA. Does that maybe still exist? I can't really see if you nod, so just shout yes or no.
I don't know. Is it like Griffins? Like
It's not Greek. So the RHA was like almost the opposite of the Greek system. It was like they basically planned like the welcome party when you got to campus as a freshman. So like, and so they were really focused on making sure anything that had to do with dorms and living on campus apart from the Greek life was successful. So like any kind of issues that were like coming up with any of the dorm housing and things like that, we kind of dealt with, but we also just organized events for on-campus residents.
Griffins?
Like,
Might have
some certain things like that, like first year experience office and certain things. I don't know about the RHA.
Yeah, it might have morphed into something else since then. Because yeah, like I said, I was there 2005 to 2010, so it's been a while. But anyway, I joined that group as well. So I was kind of involved in organizing events for campus. And then I put in these slides because these are fun. So as I started to develop into a scientist, like I said, I found the classes really hard, but once I started working with my friends in my classes, I found that to be really helpful for learning the material myself. And this is doubly true once you get to graduate school, is like working with people, kind of exchanging information, learning from them, but also teaching them the parts that make sense to you, refocuses it in your own brain. But I did work, we had the Society for Physics Students. I really don't know if that existed before we started doing things. I never attended any SPS events until we kind of took it over as leads for it. If do you all know Dr. Ginny McSwain?
Yeah,
Yeah.
she's great.
Yeah, so she's there in this picture right here, if you can see. I don't know if you can see where I'm pointing, but that picture on the bottom, that's her 15 years ago. She had just started there when I was maybe a sophomore or junior, and so she introduced having lunches for just the women in the department, which was nice. At the time, you might see some of the pictures. It was me and one other woman in most of our classes, so it was definitely nice to have sort of the building. She was the first woman faculty that was there while I was a student, at least in the physics department, so that was nice. And then this is another professor in the physics department. I think he's still there, Phil
Ooh, Phil who?
Laporta, is that the last name?
I don't know if
Yeah,
he's still here.
Oh, I think he went to Moravian or something like that, actually. He might have left. But anyway, he was a fun professor there too. But yeah, so we started like these cookouts. This is in the physics building in Lewis Lab. Us cooking outside of it and then bringing the food inside because it's clearly dark. But we also went on a trip to 3 Mile Island, and so it was fun to do that kind of stuff. So I'm hopeful you all are still doing that type of sort of community bonding within the physics department.
Trying.
It's hard. I know, organizing events and everything, it's hard. And in that same vein, so the other thing I really got involved in at Lehigh, and I think sets a foundation for how my career has developed, was doing outreach. So Dr. DeLeo, I know he's not really there anymore, but maybe does any of you know him, Dr. DeLeo?
I don't think so.
No, yeah, I think he left or retired a while ago. He wasn't really involved in active research at the time, but he was doing a lot of he was teaching, so I had him for a lot of my classes. And he was on the planetary science side, which is ultimately where I ended up. But he did a lot of outreach. So I started working with him for telescope nights for kids and talks at school. But one of the most like really memorable outreach things I did with Dr. DeLeo was that we did sort of a long-term program over several weeks, preparing 16 fourth grade girls from 2 different local schools to meet Dr. Sally Ride, the first US woman in space. She had a program specifically geared towards 4th grade girls because that's about the age where prior to 4th grade, boys and girls alike will say, oh, we like science, we like math, we like all that. And then at about 4th grade is when kids start to see themselves within the greater context of society. So that's where a lot of the 4th graders recognize that there aren't that many women in STEM. And so if they like STEM, does that make them weird? And you want to start figuring out, how to be, part of society rather than be different and in society. So it was where the pipeline basically starts leaking young girls into not being into STEM. So that's why Dr. Sally Ride focused on that age. But it was really cool because I got to work with them, and then that also meant I got to meet Dr. Sally Ride. So that was really fantastic. But I've always like stuck with STEM outreach. I really enjoy it. So I find that people, especially when it comes to space, people love space. It doesn't matter if they're 5 or they're 105, if they're from the US or if they're from any other country or any other culture around the world. They really like it. And like I said, kids, adults, it doesn't matter. And so what I try to do when I do outreach is focus on like how rather than what. And that hopefully my little contribution to people recognizing that science isn't just like someone sitting in a room and coming up with an answer. And then that's why we all should, get vaccines, for example. It's like, this is a long process. There's a lot of people that go into any kind of scientific result. And like, there's a reason we know the Earth's atmosphere and the Earth's climate is changing. Like, it's not just somebody had one answer and that's it. We got one line of evidence for that, and that's all we stop and we say, okay, we're done. It's this constant different methodology for proving any kind of science fact that's out there. And so that's sort of what I try to focus my outreach on. We do things here called, I started this program in San Antonio. It originated in New York, but it's called Astronomy on Tap. And it's where scientists go and give a couple talks about space, but at a bar. So it's fun. And we have a drinking word and stuff like that. It's pretty fun. I think there was one in New Jersey as well. I didn't mention this, but I grew up in New Jersey. I live in Texas just for the job. Yeah, in New Jersey, I think in Trenton, they had an astronomy on tap for a little while too, but that might be pre-COVID. I don't know. Anyway, so I was a student. I was doing the standard, like taking my classes, all of that. And then at some point, somebody mentioned to me that they were working on their REU application. Do you guys all know about REUs?
Yeah.
Okay. So I didn't. I think I was like really, really out of the loop of what it takes to have a career in physics and astronomy, because I didn't even know I had to go to grad school at that point. I was just thinking, like, once I graduate classes, I'm a scientist. And somebody was like, oh, it might have been Alan, actually. Alan was probably like, oh, I'm writing my REU application. And I was like, oh, what's that for? And he's like, oh, it looks really good for your application for grad school. And I was like, my what? I have to go to grad school? And he's like, yeah. And I was like, oh, okay. And now that's not true for everybody, right? So you can get lots of jobs, especially more in the straight physics and engineering side of space exploration or any kind of physics. You definitely, just having a physics degree at all is going to open insane amounts of doors for you. But to be a researcher, you generally have to go on and get your PhD. And I didn't realize that at the time. And to do astronomy, you're generally doing research unless you're kind of working at a telescope or you're on the engineering side of things. So I wrote my application for my first REU, which was at the Arecibo Observatory in Puerto Rico. And I was so excited to get selected for that program and get to live in Puerto Rico. And I really got a taste for research in planetary science. So when I was at this telescope here, which you can see, it's basically built into the karst topography of Puerto Rico. This was a 305-meter dish, so it's about 3 football fields across. And it was active astronomy. So we actually sent a radio signal out of the telescope. It would ping off of an asteroid and come back to the telescope. And because we were pinging it just like a radar device that a police officer would have to ping your car, we knew exactly where the asteroid was, how fast it was moving, and we could get things like shape models. So this is the model of the asteroid that I built using the data we got from this telescope. And if anybody ever heard of this telescope before? I can kind of see your hands if you wave them. No, nobody. Maybe. So has anybody seen the movie Contact?
No.
Oh, very good movie. I highly recommend watching it. It was the original book for it was written by 2 people, one of whom was Carl Sagan, one of the most famous astronomers. Like, he was like Neil deGrasse Tyson before Neil deGrasse Tyson. Anyway, fantastic book. It's a movie with Matthew McConaughey and Jodie Foster, and they go to this telescope. Anyway, this was the most powerful radar system in the world up until 2020, when the telescope actually collapsed. So this big part up here fell. One of the cables broke, and then another cable broke, and the whole thing fell into the dish and collapsed. And then the National Science Foundation officially closed the site about a year and a half ago now. Year ago. Yeah, something like that. Very sad. We're still fighting for it to be rebuilt, though. So if you have a passion for radio science, you can join our efforts. I can tell you how. But one thing I didn't mention at this point, but in 2007, so prior to this REU, I studied abroad. I went to a university in Chile. And when I got back from, I had done that in 2007, that I did my REU in the summer of 2008. And then when I got back from that, in that fall, again, actually, Dr. McSwain, she said to me, hey, there's an REU opportunity at Cerro Tololo Inter-American Observatory in Chile. And I guess this must have been a year. Yeah, it would have been 2008 still. So what's cool about that is, hey, I get to go back to Chile. I'm obsessed with traveling at this point because I was in Puerto Rico and I was in Chile already, and I just loved being like abroad. So like, this sounds amazing. The only caveat was that it was in the Chilean summer, which is in the Southern Hemisphere, which meant it was actually from January to March of 2009, which is when I should have been taking classes and graduating. I was supposed to graduate in the spring of 2009. And so I had to convince my mom, first of all, that I would definitely return to college if I went and did this internship, because she was like, we're so close, like you can't drop out of college. I was like, I'm not dropping out of college. I'm doing an internship so that I can go to graduate school. So I went back to Chile. I did this REU, and I had a great time. It was fantastic. Both of those pictures are pictures that I had taken, which is super cool. And then afterwards, I did a few of us from the REU internship went and hiked Machu Picchu for 4 days. So it was a pretty cool opportunity to do all of that. And then, but that did mean that I couldn't take my upper level classes that you take in the spring of 2009. And so, as I'm sure you all are aware, a lot of these classes at the upper level are only offered once a year. So I couldn't just like go back in the fall either and graduate. I had to wait until spring of 2010 to even go back to classes. And I just had a few left. So I spent a like what I call a gap year, because really I had a bunch of extra time then, and did some more traveling. So I went and I taught at a school in Guatemala, and I went back to Arecibo in Puerto Rico and finished or made more progress on the research project I had started there over the summer. Note that I also tried to study for the physics GRE at that time. And at that time, and I think things have changed dramatically, which is for the best, but at that time, GREs mattered to most universities. I bombed it. I did terrible on my physics GRE, in part because I was studying for it while I was like traveling the world and didn't care that much. And I wasn't in that like school focus mode. But in part because sometimes like the just tests aren't the best way to measure for everybody sort of how well of a researcher you're going to be. In fact, there's almost no correlation between doing well on the GRE and being a good researcher. Now, doing well on the GRE, especially the physics GRE, definitely can indicate that you're fantastic at physics. But research is a lot of other skill sets, and that's kind of, again, the theme of this presentation, than just being really good at the math and the physics. So I didn't do well in my physics GRE, and I got into graduate schools that didn't require it. I did not get into the ones, I don't think I got into any of the ones that did require it. But so I went to the University of Central Florida in Orlando for grad school. There is where I started getting involved in NASA missions. So the Cassini mission orbited Saturn from 2004 until 2017, when the mission basically ran out of fuel and they threw it into Saturn, where it would evaporate in Saturn's atmosphere. One of the cool things about grad school is that you get to present your science results all over the world. So again, this was a surprise to me that I was going to get to do more traveling. This is a cool picture of a science team meeting in Utah. But I've been to Japan, I've been to Sweden a couple of times, Finland, Switzerland, Germany, all these places, Uruguay, to present science results. So it's one of those things that you don't necessarily realize is going to happen, but when you're certainly in astronomy, probably in physics as well, in grads, when you're doing these conferences, they're kind of all over the world, which is cool. Orlando was also cool because you got to just see random rocket launches from your backyard, which is awesome. And yeah, again, I got to start studying Saturn's rings. What's fun about this is that I was doing a thing called stellar occultations, which is basically where you watch the star go behind Saturn's rings. And basically the way that the light gets extinguished can tell you about like how densely packed the rings are, like how many particles are there, what their particle sizes are, that kind of stuff. And what's funny is that little book I showed you that I had written back in 3rd grade, I actually talked about stellar occultations. You can see, I can't see it because it's behind my, it's behind my thing here. But I think I write the word, yeah, Uranus passed the star, blah, blah, blah. Basically, I described a stellar occultation in that book when I was in 3rd grade. So I thought that was really fun. But yeah, I stayed involved in outreach. I stayed involved in doing sort of community building stuff. So I was on the board of the Physics Women's Society. I helped plan the conference for undergraduate women in physics. So if anybody hasn't heard of that, those are great meetings to attend while you're an undergrad. And it just connects you with a lot of other people and a lot of universities. So if you're looking to get into grad school, it's a good way to connect with some of those future grad school programs. And just a reminder that if you're in physics and STEM, maybe you've heard this from other presenters that you've had, but grad school is usually paid for. You don't get paid a lot, but you do get paid if you go. They cover your courses, and then you're usually a teaching assistant or you're a research assistant, and so therefore you're getting paid that way too. It's challenging though to go to grad school. It's going to be 6-ish years of your life, and you're going to be living far from home, so you should pick somewhere that you're okay with spending a significant portion of your life if you are planning to go to grad school. And one of the things that I'll say Lehigh generally prepared me very well for graduate school, except at that time there was no required computer courses, and so I didn't have any computer language skills at all basically before grad school, and that is very, very important, especially in astronomy and planetary science. Everything's done on the computer. You're getting data and you're doing all the processing of that data on a computer. And so I had to learn that in grad school, and I picked it up quickly enough, so it's not like a major issue. But I hope Lehigh has classes for computer science type data analysis now. Yes.
Yeah, I think it's much more in depth. We even have like specific computational physics courses.
Okay, good. Yeah. And like I said, this was 15 years ago, but even then, I mean, it was already very important to know MATLAB or know, IDL or know Fortran or something. And that wasn't required of me at that time. So I'm not surprised, but also glad to hear that there's dedicated courses for that now. But yeah, it's challenging. Grad school's tough. And so if you're thinking about going, I'm happy to talk more about sort of pros and cons of it. And but I'm glad I did. I really liked grad school. I loved the people that I met there. Okay.
Yeah.
And so now, oh yeah, go ahead.
So were you always like dead set on grad school, or was there like a moment where you thought maybe it would be better to go somewhere in industry, get a different job, maybe not with research?
Yeah, so for me, I always wanted to do research. Like I didn't in the field of astronomy, right? I wanted to do astronomy, and really the only thing to do in astronomy besides maybe work at a telescope is to do research for it. I didn't really want to do like the applied physics side of things. I have a lot of friends from grad school who did, like they went off to Intel and work on like microchips for computers to make $1 billion, which is great for them. But I know I really never had that thought of doing that type of stuff. What I did think about doing, especially when I wasn't sure if I would get into graduate school, was more on the science education side of things. So I was looking into applying at like the Franklin Institute in Philadelphia to be like a science educator there. And yeah, I don't know. If I hadn't gotten into grad school, I probably would have gone the science education route, but maybe I would have found something more on the applied physics side. But I'm not great with like people don't let me in a lab. Like I'm not great with the engineering side of things. And so I wouldn't have wanted to do any kind of like lab work or really engineering side of things. I really am more interested in the science side, if that makes sense.
Okay, yeah. And then I had another question I'm forgetting right now, but it'll come to me.
Sure. Yeah, just interrupt whenever you think of it.
Oh, I just remembered, sorry.
Sure.
So we've heard from other speakers that grad school is like very different from undergrad, because undergrad is like very course focused, but in grad school you're doing research. What was that adjustment like for you? Like, how did you like it, and maybe what were some of the challenges with that?
Yeah, I'd say one of the biggest challenges in general for grad school, and then also a career in research, if that's what you end up doing, is time management. So like in undergrad, you have a class and you have a test, or you have a project or a homework that's due in 4 days, and you can procrastinate all you want, but within the next 4 days, that homework assignment has to get done and turned in. And That's not the case when you're doing research. A lot of times the project you're working on is something you're going to work on for 2-3 years. And so you can get away with like doing 0 for a long time. But if you're not self-motivated to be productive, you won't get it done in time though, right? So like you'll have a conference, for example, to present your work at 3 months away. And so you're like, oh, I got plenty of time. If you're not able to like regulate yourself and and make sure you're spending 6 hours a day or something working on it, you'll find yourself in 2 months trying to panic and try to throw it together really fast. And it doesn't work like that. You can't do that same procrastination that sometimes you can get away with for homework assignments. And so really time management is a really key skill that you learn. You have to learn to be successful in grad school. And yeah, like I said, I mean, you're not usually like having to do a test. You have some classes still in grad school, so you do still have some tests. But when it comes to research side of things, it's really about like the diligence and like thinking about different ways to solve a problem. And so it's not just like, okay, there's a right answer here. Like, no, in fact, when you're doing research, the whole point is that you're exploring a question that doesn't have an answer yet. And so there is no right answer. And so you have to be willing to like go down the wrong path for a long time and accept that you went down the wrong path and backtrack and try a different path. And so that can be really hard too, to like accept that, like you can put in like weeks and weeks and weeks of work and realize that's not going to work out. That's not the way to solve the problem. And then you have to just accept that you learned something from that, but like that you're not any closer to finishing your project now. And so, yeah, so there's a lot of those kinds of differences than there is when you're just a student taking classes.
Okay, makes sense. Thank you.
Yeah. Yeah, so I'd love to talk more on grad school stuff. I don't know how long y'all have, so I'll just kind of go through the rest of my the rest of my slides, and then you can ask. I'm happy to talk more about grad school. But so after grad school, I graduated. Typically what you do is a postdoc after grad school. And so I ended up at the Southwest Research Institute, which is here in San Antonio. It's a not-for-profit institute with scientists and engineers doing work from Department of Defense stuff to biology, chemistry, robotics, oil and gas, tons and tons of stuff. But there's also a space science division here. And so what you see in this picture up here is actually the development of one of our UV instruments I think this is the JUICE one. So this one is currently in space on its way to Jupiter on a European Space Agency's JUICE mission. And so we do a lot of the instrument building for a lot of the NASA missions and the European Space Agency missions, which is really cool that we get to do that here. Oh, and that's oh, maybe that one's UVS. That one might be because this one that I just showed is mass specs. That's an instrument that's going on the Europa Clipper mission. And so what I do at SWIRI, I really do see myself as like combining a lot of diverse skill sets. So what I've been trying to kind of say as I go is like, I learned the science, I took the classes, I passed the classes, I found them hard, but I passed them. But really by doing things like the RHA, by doing SPS, by being involved in research, I started really diversifying my skill set. And I think that I became someone who could really communicate science in addition to also just being someone who could do the science. And so those skills have kind of set me up for leadership positions. And that's really, I think, the main reason why I kind of quickly became a lead on some of these instruments in some of these missions. And it's really because I'm able to organize well and kind of synthesize data, synthesize information, and figure out how we're going to tackle these problems. So that's a different skill set than it is to be able to, do the math or do the science on a specific scientific question, right? You have, in order to do some of the team building and team leadership side of thing, you also have to understand how to work with people. And so that's why I'm trying to say that a lot of these different experiences that I've had, both in communication and outreach, and also working as a leader on like the RHA and doing things like building a party for freshmen in college, it actually all kind of built up into being able to organize people and scientific goals and activities. And so Yeah, and then I still do a ton of outreach. I just led a huge effort to do all of the eclipse observation, letting the community know that there was going to be a solar eclipse right over their head, 2 weeks ago. And yeah, and then in addition to that, I'm still doing the science side. So I submit NASA and Hubble and James Webb science proposals so that I can do scientific research. Really quickly, I wanted to at least talk a little bit about Europa Clipper. So this is the NASA mission to explore Jupiter's icy moon Europa. And this moon is an ice shell, but it has more liquid water than all of Earth's oceans combined underneath that shell, ×2. So there's a ton of water. So if there's anywhere in the solar system to check for life, this is the place to do it. The mission is officially not a life hunting mission, but it's an investigation of the habitability. So what is the ocean temperature? What is the ocean salinity? What are the other components of the ocean itself? It's not just pure H2O. Is it what salts are in there? Is it salty like our Earth salt composition? Is it more like it has potassium, calcium? What are all of the different materials that are inside that ocean? And so I do a lot of the mission operation planning for our instrument, the UV instrument that I work on. And at the same time, my science interest in it is understanding the composition of Europa's atmosphere and its surface using spectroscopy. So looking at the UV, but also looking at basically across the UV. So we get these, I don't know how familiar you are with spectroscopy, but basically on the surface and in the atmosphere, you'll see light being absorbed at certain wavelengths. And that absorption, those absorption features or emission features, if we see aurora, can tell you directly what material is doing the absorption, because it's going to be a certain frequency that matches the atomic makeup of the gas or of the surface. And so we can tell something about the composition of the surface and the atmosphere by looking at how the light gets affected by the material. And so that's the type of research that I've done a lot of in the last couple of years. So this is an example of a spectrum. This is wavelength along here, and this is reflectance. And you can see that, if the sun's getting brighter as you go along in wavelength. And so if there was nothing of any compositional interest there, the spectrum would probably follow something like this red line. But the fact that there's this big dip here is indicative of the composition. And so in this case, this is probably SO2 on the surface absorbing part of the sun spectrum. And but what's interesting about Europa is that Europa's surface sort of looks just like water ice looks like, but with some differences. And then you can see on the leading side of Europa, it's very, very bright. This is mostly just water. But on the trailing side, it's darker, and that's probably material like SO2 coming from Io and getting smashed onto the surface. And then here's just a map from one of my papers that shows sort of what how deep this band gets, tells you how much there is. So on the leading hemisphere where it's blue, there's no sulfur, and over here where it's red, there's a lot of sulfur. But anyway, if you want to be part of a mission like this one, now's your chance. So we launched this year, but we don't get there till 2030. So the science analysis of this is really going to be happening not for another 6 years. And I just kind of want to highlight the different roles that go into a NASA mission. So there's the engineers, mechanical engineers that build the instrument, electrical engineers, make sure it all works, software engineers. Basically, we work with them directly to be able to command our instrument to operate and take the data the way we want it to take. Systems engineers, making sure all these parts work together. Orbital dynamics experts, so if you're really into the math of like figuring out, where does the spacecraft have to go to reduce the use of energy, and how is it going to orbit Europa? And if we put a little bit of energy out at this time, a little bit of thrust, what's that going to do to our orbit? I'll note I just said around Europa, but this mission actually orbits Jupiter and does close flybys of Europa. Of course, there's the scientists who are highly interdisciplinary for a mission like this. So planetary science, like myself, but astrobiology, since it's related to life type mission, ocean and marine scientists, geologists, all of that goes into a big mission like this one. And then, of course, non-science roles like communications team and administrative, contract management, program management, and more. And just real quick, sort of how a mission or any science project really gets developed is to kind of start with NASA either saying, hey, where should we explore and why? Or NASA says, hey, we have a mission, we have a target, like their next big mission is going to be Uranus, sell us on your instrument, sell us on your idea. And then so you get the team of scientists that write one of these proposals. So it's a lot of writing to write a proposal that's successful. And then you have admins and contracts experts and graphic designers that all help you develop your proposal. And of course, a team of engineers to build whatever instrument or mission you're working on. And then this sort of a recap of all the different jobs I just mentioned, but all of these people have to come together to develop a strong proposal before that can get submitted to NASA. And then NASA reads through a bunch of them. And by NASA, I mean the community. So anyone who has the right expertise. So I will often go on a NASA panel and review other people's proposal ideas. If I'm proposing to that program, if I'm someone trying to sell my instrument or my science case, I'm not allowed to be on that particular panel. But if it's a case that I haven't proposed to, then NASA can pull me in to do the assessment of other people's proposals. And so, yeah, just as a kind of final summary, so my job that I typically do is I write these proposals to obtain funding from NASA. That obviously means that in addition to knowing the science, you have to be able to communicate, you have to be able to write. You can design your own graphics or work with a graphics team to kind of show and sell your proposal. It's really a lot of salesmanship in that. Once you win the proposal, so that AKA they fund you to go do your research, then you conduct the research. Obviously, that's where the science, the math, the computer skills are really important. And then you're working with a team. You're rarely doing a project on your own. So this involves teamwork, leadership, delegation, and of course, the science to actually interpret the data. And then you present the results at all these conferences all over the world. So presentation skills, making a PowerPoint, communicating your idea in a way that makes sense. So that people remember what you've said and can then cite your paper and publish the results. So basically, in the world of academia, publishing is really important. So how many papers do you have? How many times does that paper get cited by other papers? That all matters a lot for sort of your status in the community, I guess, in some ways. But again, so you have to be able to write and communicate in a way that other people can understand what you're talking about. And then I like to communicate it to the public. So presentations, sometimes if you have a really cool result, you're going to have to talk to reporters or the press. And so you can see that there's a lot of stuff that requires a lot of other skills besides just the science and math. And of course, the science and the math are critical. This one step is not a trivial step in all of these steps, but having other skills really is important. And so, I did want to just add that I have a family too. So that happened along this career path. And actually we just met Bluey last weekend. So that's why this picture's here. But I did the little one in this picture is that size currently. He was born in January of this year. And our first was born in August of 2021. And then, so my final tips as my parting information is that one, don't compare directly any one skill with anyone else. So when I was at Lehigh, I really did struggle with some imposter syndrome and feeling like, oh, everyone else around me is just so much better at this class and they're getting A's and stuff like that. And then one time, I actually had a professor at Lehigh. I don't know if he's still there, Dr. Honeykins. He was like, you're doing great too. Like, there was this one class where everyone else was just doing really exceptionally well. And he was like, if you were not in this class, but in last year's class, you wouldn't feel like you were at the bottom of the pack right now. This particular class is doing really well. Don't compare yourself to everyone else, because really it's the conglomeration of your skills, expertise, and experience that are going to ultimately play into whether or not you're successful in your career. And then research isn't the same as taking exams, which is the question that I got. So get involved in research early though, to develop those skills, because they're probably going to be more important to a grad application, but also to your, if you go into any kind of a research field, they want to know that you can do the job, not just do well on an exam. So any kind of experience that's going to be similar to the job that you end up doing, if you can show that you're capable of doing that type of work, that's going to be more meaningful than any kind of grades that you can get. And learn how to do research. So I was saying earlier, you have to try several paths and options. You never want to just go to I would recommend not just going, unless you're totally stuck and you have no idea what to do. still try a few things, show that you've made some efforts and what directions you took, and then your professor or your advisor or your employer can say, okay, I see that you've tried a few things. I see where your brain was at when you and how you tried these. And now I have more information to guide you in the right path to try or how to push forward in one of the paths that you tried and got stuck on. But if you're kind of just like, I don't know what to do at all, that can be really hard for your advisor to guide you because they don't even know what's got you stuck. So showing that where you've gotten stuck and then how you've tried to get yourself unstuck goes a long way. So that's sort of just my tip for if you're in any job really, but in research especially. And then find the holes and fill them. So when in my career, I feel like one of the things that I have done well is, I got involved in the NASA mission. I feel like that was partly luck. But once I was in the mission, I said, okay, this is an area that really is important that it gets done, and I'm just going to take the initiative to do it. And then once you become the person that's always doing that, that did that role that was critical and did a good job at it, then you become indispensable. And so that was sort of my path of getting involved on these missions was, hey, there's a hole. Let me make sure that gets done. I'm going to do the best I can with it. And I'm going to just show it to the boss, to the lead. And that person was like, oh, I'm so glad that got done. Like, thank you, And so that's my tip for kind of getting involved into any project that you're really interested in and making sure you stay involved. So, yeah, so I have other slides, but those are sort of backups. So I'll stop there in case you guys have any more questions.
I was curious to, I guess, hear more about your graduate school experience. You said time management was a big thing. How did you time manage? Like, were you always an RA or did you TA for a little bit? Like, how did you manage with the class, like teaching or grading and stuff like that with the research?
Yeah, so that part is hard. So I did both. When I started, I was a teaching assistant my first year, which meant that I was in like a lab setting and I had to grade a lot of assignments. It's really hard. And it's hard because I'm someone who does generally care about the students too. And so like you want to do right by them. I'm sure you all appreciate that if your TAs are doing right by you. And so you want to make sure that you're spending the right amount of time grading appropriately and answering questions and everything. And so it's hard to balance that with your research at that time. And so it's generally understood that that first year while you're taking classes and you're teaching, you're not really expected to do too much research at that point. But even finding the ability and the time to teach while also having really challenging classes, right? You're in a graduate level course is hard. And so it's really just, it can be a little bit of a system shock at first, to be honest. And then you kind of just have to figure it out and figure out what works best for you in terms of, sleep. When do you make sure, do you work well in the mornings, wake up an extra hour early, or, are you going to work late in the evenings? And that's okay too. And just finding the right time, but it is really hard. And then I became a research assistant after a year. And yeah, you still have to balance that with classes. I would say that once I had a real job, I became a postdoc, even though there are weeks and months sometimes where, there's a big project, big deadline coming up, a big proposal deadline, and you work like way more hours than a 40-hour week. There was a huge difference from grad school to having like an official job, a 40-hour-a-week job. If you're a professor, those lines might still be a little bit blurrier too. But as a student, I just felt like in grad school there was like never ending to your work. My mom was a nurse, and she, at the end of the day, she puts her pencil down and she goes home, and she doesn't have to think about work again until the morning. And that's just like not how it is in grad school. You're gonna always be thinking about it. Yeah, so you really just have to learn how to make sure you can get it all done. And it's not easy. It's not easy. But that's why I said like working with other people, somebody to commiserate with your friends, but also to like pace yourself too. Like you're going into the office with them and they're working and you're working and you all take coffee breaks together or whatever. But it's definitely not easy.
So would you say that maybe even now that you have more free time or you better time management skills than in grad school?
I think I have better time management skills for sure. I think I developed that through grad school. I think also having more of a family makes you delineate your time a little bit better. So I don't know that I have more free time per se, but you know, at 5, 6:30 p.m., I don't usually open my laptop again until I go to work the next day. And so that does really kind of cut you off from working. And then that's my family time, that's my friend time. But when I was in grad school, I felt like I was just kind of always working, but not efficiently, if that makes sense. So I had friends who were better about it, that were efficient, that they went into the office from, you know, 9 to 7 or 9 to 6, and they did their job 9 to 5, researched, and then put their computer away too. But that wasn't me. I was sort of always like, you know, I was maybe there from like 9:30 to 6, but I was talking to friends, or I was on, you know, on Facebook or Twitter or something too. And then it was like, oh no, I didn't get as much done as I wanted. Now at 10 p.m., I'm gonna reopen my laptop and work a few hours. So it really just kind of depends on what you're able to do.
Okay, makes sense.
I had a quick question. I was just wondering if you could kind of explain like how you went from like working at like the Southwest Institute, if that's what it's called, to like working on rover permission at NASA. Like, is that like part of the Southwest Research Institute, or is that like something separate? Like, are you
Yeah. Yeah, so that's a great question, because I think a lot of people, including myself, assumed that like you work for NASA or you don't, right? But that's not really the case at all. So a lot of the majority of the instruments that are on NASA missions are built by universities or by other institutions that get added to the mission. So NASA runs the mission. In this case, it's run out of the Jet Propulsion Lab in California. And they also built some of their instruments. So JPL has scientists and engineers as well, but they built 2 of the instruments there, but the rest of the 9 instruments were built at so Southwest Research Institute. We built 2 of them. There's one built at the University of Arizona. There was one built at the University of Texas in Austin. There's one built in University of Colorado in Boulder. I'm sure I'm missing a couple places. One's being built at the Applied Physics Laboratory, which is another like institute but that's government run. They built one of the instruments. So all of these instruments get built all over the place, and the scientists can be from those institutions where the instruments are built or not. So if you could be a scientist, you could be a professor at Lehigh and be a scientist and be involved in the mission if your expertise, you know, got you on that mission. So if you were working with one of the instrument teams from the start, even if you can't build it there, but you're the world's expert on Europa's saltiness, you might still be part of the team remotely. And so, yeah, so basically the scientists and the engineers working on this NASA mission, only a handful of them are officially NASA employees. A lot of the engineers that are putting the spacecraft together are NASA employees, but those building the individual instruments are from all of these different universities and institutes across the country.
So if you would like if you wanted to like work on one of these missions, like would you recommend like trying to like work for NASA, or like for going to one of these universities or like research institutions?
If you want to be an engineer, if you want to do like the building side of things, working directly for the Jet Propulsion Lab or Goddard Space Flight Center, those are the types of places where you're kind of going to be guaranteed to be doing hands-on engineering for a mission. If you want to be a scientist on a mission, there's really not, I would almost say, don't work at one of those NASA centers. There are scientists at the Jet Propulsion Lab. I mean, one of them is running the mission, so it's not like there aren't scientists there. So you could be a scientist at Jet Propulsion Lab. You could be a scientist at Goddard. But the majority of the scientists on the mission are at universities. And so what you'd want to do is a university or like a research institute like Southwest Research Institute. You'd want to make sure you're at one of the big named universities that are involved in previous NASA missions. So University of Arizona, University of Colorado Boulder, University of Maryland does more of like the space physics side rather than planetary science side, but they build some stuff, or they're involved in a lot of things. University of Central Florida, where I went to grad school, they're involved in some of these missions as well. Trying to think, University of New Mexico, there was a scientist there that was really involved in the DART mission that smashed into an asteroid. So there's a bunch of those types of missions. So you would look, what I would do if you're interested in the science side is look up some of the missions that you're most interested in and see where all of the instruments were built and see where the head scientist works. And that will give you an idea of kind of what schools to apply to.
Thank you.
Okay. Well, I don't know if we have any more questions, but thank you so much for coming to come talk with us.
Sure, yeah, and if you think of anything or you want to be in touch or you want to learn more about Europa Clipper, I have just my website here, but I'll put my email down here at the end so people can see it too. So yeah, if you ever want to email me or something and just say, hey, I'm one of the people at Lehigh, I'd love to talk more. I'd be very happy to. I really loved, yeah, I was excited to give a talk to other Lehigh students because I really did love my time there and I haven't been back in so long. But it's a great school. So I hope y'all are having fun there.
Yeah, definitely. Well, we appreciate it. Have a good day.
Thanks, you too.
Thank you.